Wednesday with Alex talking about experimental and observational studies in the presence of stochastic networks. We have 45 minutes.
Thank you, all of you, for braving the rain and for getting your shoes wet. Hopefully by the end of the talk, my shoes will recover and be the correct color. I want to thank Ben and Alex for organizing this. It's been really, really good. You might be confused by why a statistician is here. And
Nicole and other.
What?
Nicole and other.
And Nicole and others, yes. You might be confused why a statistician is here. It's mainly because I want to learn about some of the things that have been talked about today. And I think some of the work that we're doing sort of jives nicely with the work that has been presented so far. So the talk today will be a little bit different than what we've seen the last 2 days, but I think that there's some nice symbiosis that we can all learn from each other. So sort of the big picture that the world that I live in is we have complex problems that we're interested in studying. These are causal problems. We want to run experiments. And it turns out that running an experiment is no longer feasible just by flipping a coin and doing an A/B test. That doesn't give you the answer that you want because there's this weird complex social behavior that's happening behind the scenes, and it might be tainting what you think you're learning about. And so there's a ton of literature that's been coming out over the last 15 years in statistics and causal inference and econ and CS, dealing with notions of interference, the fact that my treatment might affect my friend's outcomes, homophily, the fact that my friends might behave similarly to me, contagion, the fact that things happen over time, and sort of lots of other different problems that networks bring along. And one of the sort of guiding principles of this literature has been that there exists a static network where we're interested in doing sort of a static experiment. And the first part of the talk will give you an example of how you might go about doing that type of experimentation. But the reality is that everything is stochastic in our world, and we have lots of sort of reasons to worry about the fact that networks might change. And so your interference might stochastically change, your contagion might stochastically change. And how do you deal with that is sort of interesting. Sort of the way that I've thought about doing experimentation has been in this context of model-assisted design, where I postulate a model for the universe, not unlike many of the sort of simplified models that people work with. And I try to come up with an experiment that will perform well without actually regard for the model when I'm doing the estimation afterwards. And I'll sort of make that clear in a little bit. The problem is that when you have dynamic networks, things become hard. And so how do you incorporate these dynamic network models into the model-assisted design is sort of the next stage or the next phase of this universe. And what do you do in observational studies? That's sort of a whole other problem. All right, so I'll give you two motivating examples. This is stuff that I've worked on. I think we can all agree that people infect people, but in fact, actually one person infects one other person. It's not sort of a collective action. But when you're studying whether or not masking works or vaccines work, you need to account for sort of all of the interactions. And you can't see here in gray, but there are connections between these people. And these are real people in a real college campus. And they were interacting with each other. And then the flu happened. And some of these people were instructed to stay in their room. If they had symptoms, some of these people were not instructed to stay in their room. And we wanted to see whether or not that type of isolation was useful. And the thing is, without accounting for the fact that there are network ties, it's kind of meaningless to think about this intervention, because the whole point of the intervention is cutting network ties. So how do you do that? You have to account for the network process that's under. In a different universe, I think a lot about political polarization. And this idea sort of comes out of the fact that over the last 20, 30 years, or 40 or 50 years, we've sort of become very familiar with the idea that Americans are just divided on pretty much everything. And what's interesting is that unlike in the 60s, 70s, when actual socioeconomic or demographic principles were predictive of policy positions, now partisan ID is substantially more predictive of position. And so we're interested in understanding whether or not there's something to blame for this. So there's been a hypothesis that echo chambers are to blame, that we just sort of self-isolate and that we don't expose ourselves to opposing views. And so the follow-up hypothesis to that over the last decade has been maybe social media is to blame. Well, so how do you test whether or not social media is to blame? You are necessarily dealing with some kind of network process. This is a picture from an experiment that we ran on Twitter, and our goal was actually to collect unconnected individuals. We went to a survey firm that promised us this is a representative IID sample from the United States. We can discuss sort of later whether or not anything is a representative IID sample of anything, but we were not expecting these people to be connected on Twitter. And as you can see, they were definitely connected. If we were to have ignored this portion, we could have introduced massive bias into any kind of study that sort of is interested in understanding whether or not selective exposure is doing something.
Are you going to talk more about this, or?
I wasn't planning on it. This is sort of just as a motivator, but I'm sure.
What would you have expected? Is this more likely to be a rejection of the null hypothesis that they were sampling correctly, or is there a reasonable process for Twitter linkage that would actually have produced this?
I probably don't really want to speculate on camera too much about what is going on behind the scenes of these large survey firms, but I will hypothesize that one of the reasons these people might be connected is because they are participants in a survey. And in fact, I'll give you 3 seconds more on this. So these are clearly colored by partisan ID. The middle of the blue one is some kind of journalist, and I don't know why they're responding to surveys, but good for them. And the middle of one of these red ones is somebody whose Twitter handle we would not be able to put up due to, problems. Yeah, I think that there's something's driving that, but yeah. Okay, so this talk is probably too long, and I'm going to try to de-jargon it as much as possible. But sort of the first half is this idea that we want to do high quality causal inference. We want to design experiments. That's part of something that we control, sort of how we randomize people into A or B and to test a treatment or control. And then the second half is going to be how do you leverage stochastic modeling to really improve some of these experimentations. What I hope to get out of this talk, so this is for you, this is for me, I want to sort of understand how these things connect with the literature that has been described really nicely the last couple of days. And the other thing that I'm going to have one slide on at the end, we have a nice experimentation platform that we've been developing at the Polarization lab that I think, based on my understanding of the last couple of days, is something that could be very useful to validate some of these very interesting sort of equilibrium results that people have been presenting. So we hope people will be able to use it very, very shortly. All right. There's too many collaborators to name. These are sort of only people that were directly on the papers that I'll sort of bring up, but there's a lot of other people in the Polarization lab and some more fantastic students. Fian Bu's on the market this year. Everybody should hire her. Faye will be on the market in a couple of years. Yeah. All right. So this is probably one of the first times that I am presenting causal inference at a workshop where I think I'm the first one to talk about causal inference. So I'll give sort of a quick background on what it is I think of when I talk about causal inference. I think of it in the potential outcomes framework. There exists sort of different universes, and individuals might be assigned to some kind of treatment. And we'll think about treatments as binary, 0 or 1. And a potential outcome for a unit is indexed by all of the treatments of everybody else. And so that means that there exists 2 to the n possible different types of universes that any one individual could experience. Clearly, that's really, really hard to work with. We can't really do much with that. And so we make lots of simplifying assumptions. And so the standard assumptions for the first 80 years of causal inference has been some version of an individualistic treatment response or SUTVA or whatever we want to call it. And essentially, it says only my treatment affects my outcome. And so suddenly you went through from a 2 to the n space to just a 2 space, which is nice. Once you do that, you can start thinking, well, what is it that I actually want to learn about? And people frequently want to learn about average effects. So this is the average over the individuals in the sample or in the population that you care about. And it's the difference between their two things. But obviously the curse of causal inference is that you only observe one of the two universes, right? You either observe somebody's treatment response or their control response. And so much of the work has been sort of spent on explaining why estimators like this are good. And it's probably fairly clear. You don't need to have a background in causal inference to really understand why this is good. This is probably going to be a consistent estimator of the average for the treatment people, right? If everybody is IID sampled from a population, if randomization happened, everything is good, then this will be a good estimate. Similarly for this, for the control people. We sort of leverage two things, right? We leverage the fact that we can either randomize or that we might learn the selection mechanism and use this. Networks make this necessarily more difficult because suddenly this might not be a viable assumption. And you are sort of going to have issues with whether or not your randomization is inducing some kind of interference or whether or not it's inducing homophily or it's being manipulated by the homophily and so on. And in observational settings, it's like way, way worse. You have to make way stronger assumptions or you need to have way more data. But we want to do causal inference on networks because we're interested in studying disease prevalence, social development, business transactions, and so on. And so we need to sort of deal with this. So homophily interference are sort of things that people have been thinking about. There's this third thing that I won't have time to talk about, but it's this idea that you can't actually give treatment to only one agent. You have to give treatments to multiple agents simultaneously. Turns out that makes things way, way worse. That's for future problems, but we have a nice paper on that with Panos Toulis and Edo Irobi. So we can't make this simplifying assumption that Z1 through Zn are somehow not going to affect, oh, sorry.
What is homophily statistically?
So homophily here would mean that my outcomes are correlated with your outcomes if we're friends, for example. So it's some kind of correlation. I haven't put any model on anything yet. I'm just sort of, yeah. So homophily is birds of a feather tweaked together, right? Similar people behave similarly. Interference is I give you treatment, we're friends, and so I get some kind of outcome change because of that. All right, so we can't make a simplifying assumption. And the other thing that's no longer clear is what are we actually trying to learn from these experiments? Before, average treatment effects were kind of meaningful. Conditional average treatment effects is something that has been sort of all the rage, or heterogeneous effects or individualistic effects. But what can you actually learn when you have a network? Because you suddenly need to contrast things that sort of are in 2 to the n type of space, which is not obvious. So a very popular effect is this total network effect or the global average treatment effect, which contrasts everybody treated versus nobody treated. We will be interested in sort of the effect of isolation or the value of isolation, these direct effects. Does the vaccine protect me actually? Indirect effects or sort of the social influence or the peer effects literature has been interested in what happens when my friends are treated and I just sort of exist in a vacuum. And the sort of the combination of these two is some kind of herd immunity or total node effect. And the problem with this universe versus the naive A/B test universe is that I'm going to make the argument that you need to make a decision on what you want to learn before you can run the experiment. And once you've run the experiment, it's extremely unlikely you'll have access to all of these estimates. Because some experiments are just unable to give you access to more than one. So what we want to estimate, we might be able to control. We might be able to control how we randomized individuals into treatment. And we have a control of how do we want to summarize the data, the estimator. And sort of on the side of doing honest causal inference, we should fix as much of this as possible a priori. And so the estimand presumably needs to be fixed. We need to know what we're studying before we run an experiment. I'm going to claim we should probably fix an estimator before we run the experiment as well, so that we don't p-hack our way to an answer. And so then the only thing we get to sort of play with is this randomization scheme. Can we design a better experiment by changing how we randomize people into treatment and control. So there's early work in the causal inference literature, and I realized that I did not update these slides with all of the relevant Mansky references. Mansky has similar papers in the 90s and 2000s as well. And so this universe considered two-stage randomizations where you had separate groups. There's interference within group. There's no interference across groups. Turns out you can run an experiment and study lots of stuff that way. This really nice work by Ugander et al. Is sort of the first time that people really carefully, as far as I can tell, work towards an experiment that's actually motivated by the quantity they're interested in studying in the network section universe. And they were interested in total network effects. And they showed that this notion of graph cluster randomization works really, really well. So you take a giant graph, you construct small microcosms of your graph in there by doing some kind of smart clustering. And then you treat each of these as a representative subgraph. And then turns out that gives you access to total network effects. It also is very clear from that setting that it will not give you access to direct effects, because you no longer have people who are treated who don't have any treated neighbors around them, right? Because you've now treated whole neighborhoods. So you can run this experiment, but you won't be able to learn anything other than this. We're going to be interested in direct effects, and we're going to make a simplifying assumption that interference and homophily are going to be restricted to the neighborhood of a node. This is just for ease of exposition. This can be done sort of in more generality later. This is a notation-heavy slide. I just want to sort of set the stage. We have 2n agents or nodes in our graph. I'm going to have to divide by 2 later, so that's why there's 2n of them. N is the neighborhood, D is the size of the neighborhood, and these are sort of quantities that exist that describe the universe for this individual. So there's some kind of direct treatment effect for a participant, right? So this is the truth that would have happened had they been treated and nobody else around them is treated. There's some kind of function that summarizes how the treatments of their friends affects their outcome. And then maybe there's some kind of baseline effect or covariate effect. And if you have T as the set of treated units, this is the type of model that's going to motivate our work. So this is a very simple model. It essentially postulates that everything is additive. But what's important is that at no point we're going to try to estimate the model itself. This is just going to be how we're going to, the universe under which we're going to evaluate a very naive, simple estimator that doesn't know anything about the model. Yeah.
What was vertex covariance?
Yeah, so just think about that as baseline effects for a person. So this is the fact that you just might be different from me in baseline.
That function as a function of the subsets. That's very general, right? I mean, that means that I don't just care about the number of affected treated neighbors, but also combinations.
That's right. Yeah, so this is
Why would you do that?
because it might be the case that some kind of interference is not just based on how many friends you have that receive treatment. It might be because of the fraction of friends you receive treatment. That's sort of a simple version of that. But it could be
Much more general, right?
This is much more general. That's right.
Yeah.
It could be so we have even further extensions of this where it's even more general. Maybe because you have friends who are also friends with each other, that's more powerful interference than if they're not connected to each other, right? So that's sort of leveraging some literature from sociology. So I assure you, we will have to simplify this a little bit in order to actually get the theoretical results we want. But sort of currently, it's very general.
I just understand it a little bit more. So the simplifying assumption there is that the actual effect is coming from the treatment of my neighbors and not their actual outcomes.
Yeah. So this is.
So what kind of applications are ones where the treatment is what affects my outcome and not the outcome?
Yeah, that's a good question. And sort of this, there's a little bit of confounding between notions of interference and contagion. and it's usually analyzed sort of simultaneously. You can think about get out the vote type of experiments where it's the sticker that you voted. I don't care if you actually voted. It's the fact that I gave you a sticker and you showed me the sticker. So that's not the actual outcome. It's the I allowed you to show me the sticker.
What's the experiment would be testing the effectiveness of stickers? Or?
Yeah, the effectiveness of the badge that your friends voted. Did it make you vote? But I agree with you that this is sort of one of the reasons why it's important to move towards a more stochastic version of these. And a lot of the analysis that sort of those previous literatures have been doing is exactly in the setting where things are static. And that might be insufficient realism. Okay, so our goal is going to be estimating sort of the average over this population of these T's, right? But we don't have access to the F's. We just have a way of controlling who gets treated and who doesn't. And the other thing, and this might be sort of deviating a little bit from our universe, we're interested in the naive estimator. This is a difference in means estimator. It's the same one that we had on the first slide. And the reason we're interested in this estimator is because it's really easy to explain.
I didn't have a question.
The example with stickers, so you're saying that like if I get a vote,
Yeah, so that's
sticker, I'm more like you want to test the probability that I then am gonna vote if you already gave me the sticker.
yeah, no, so that's a bad example for the direct effect because they were interested in pure effects. So a direct effect might be, I advertised to you about a particular, I gave out flyers, and I'm interested in whether or not you did what you saw on that flyer versus if you're doing something because your friends got the flyers.
You can make the time frame. You can make the time frame narrow enough that
Exactly.
it wouldn't be likely to be because of the purchase that like.
That's right. That's right. Yep.
Like why you are restricted to the averages as opposed to something like inverse propensity score?
So why am I going to use this estimator? So the first thing is, so the question sort of is why use this instead of like an IPW or something more sophisticated. This is easier to explain. When you open the New York Times and you read the outcomes of an experiment, this is more likely to be explainable. The other issue is that, well, the other thing is that we're doing sort of an experiment, so we hopefully don't need to inverse weight by anything. And the last thing, and that's sort of my own soapbox, inverse weighting blows up variance. You can obviously correct for that, doing some kind of Hayek thing, but nonetheless, you're going to end up with something that might be unstable, especially in this network universe.
But there's still something a little funny. I mean, you would think somehow I would have thought statisticians would say to do anything, and then you would worry about all the things that you said you should worry about, rather than just saying we're going to focus on this one thing.
Well, so if I fix this, then I can tell you how this estimator behaves under different randomization schemes. So it's true that I could not fix this and try to study. I could try to overfit to this model, but I don't want to do that, right? So I want to study how does this estimator behave under this type of universe.
You probably said it already, but why is the average treatment effect as defined? Why is it interesting if you ignore the editor?
Yeah, so it's sort of this value of, so this is the average direct effect, right? And it's the value of isolation. So you could be interested in, imagine you have some kind of vaccine, there's some kind of zoonotic disease, you want to go and vaccinate people in a place where they're not likely, it doesn't matter if their friends are vaccinated or not because they live on a remote island. So I'm interested in, does the vaccine prevent zoonosis, for example? Yeah, but all of these are very good questions. And what's interesting and important here is that I think that the universe that we live in is somewhat limiting because once I construct this randomization scheme, you're not going to be able to learn about peer effects because I'm going to get rid of the peer effects by design. And so one of the things that a few students and I have been working on is how do you design experiments that are flexible enough to give you access to more than just like one thing. And it turns out to be really hard. This is sort of just motivating this type of linear model. This is too much notation, but essentially this linear model corresponds to some decomposition of potential outcomes. So this is in fact a causal quantity. It defines causal quantities, and you can think about sort of this TV as this type of direct effect and so on. I'm happy to go back to this slide later, but this is sort of just justifying that we're not making stuff up. All right, and so this is our operational quantities. So we're interested in this average direct effect. We're going to use this estimator. The best estimator we could hope to use is this one that actually knows things about baseline characteristics and that knows exactly how much interference there is. Obviously, we don't have access to the interference, but the difference between this estimator and this estimator is telling us something about how high quality this estimator is, right? So if we can bound C, it's the same as bounding the error in our estimation, depending on what F is. We're going to try to bound the first and second moments. Yeah, so it's ideal because it knows kind of a lot, right? So it's for everybody in treatment. It knows it has essentially decomposed the outcome, the Y's, into the parts of it that are the direct effect and the interference effect. And so it's essentially thinking about, for treated people, I do Y of V minus their interference. And for the control people, I do Y of V minus the interference. So it's ideal because it's sort of the oracle that knows about the interference. All right. And so what's, in my opinion, really cool in this result is that it's a really easy design. So remember, I have two end nodes. I'm going to suggest that you partition them into pairs however you want. I'm going to assign one member of each node to treatment and one to control. Under some sort of simple Lipschitz assumptions on the interference. So again, we're very general still, which may or may not be useful, but it turns out to be sort of exactly the type of Lipschitz assumption that is used in the literature when people actually fit models. So linear interference is gamma d Lipschitz. Fractional interference is gamma Lipschitz, and so on. So it's an assumption that if I didn't have to, I wouldn't make, but it's also exactly what people fit when they fit models without regard for the actual design of the experiment. And what's really, really cool is that I can bound the bias in the estimator. So these are the Lipschitz constants, and this is a sum. So the bias of the estimator, of the naive estimator, is bounded above by a sum, not over the full graph, not over everybody who's connected, but over people who are connected who also happen to be in my partition set. So they're paired together in the partition. And then this is sort of standard stuff that comes out of much network analysis. But that's A, surprising, and B, really, really encouraging, because it means you can design a completely unbiased experiment under this extraordinarily complex potential interference. You can just pick your partition so that it is not, doesn't include any edges in your graph. And then suddenly you're unbiased. Now, maybe that's sort of not enough for us. And so that's where we're going next. But in reality, this is very powerful. If you're Facebook and you're running 1 billion of these experiments, and for some reason you care about direct effects instead of total effects, just do this. And suddenly you are guaranteed an unbiased estimate. This bottom sort of just is a recovery of existing results. It says that if you randomize over pick this partition uniformly at random, you get this type of bias, which is exactly what people have been doing in the literature. Okay, so are all partitions made equal? And I'm going to claim that they are not. So again, remember, our goal is to remove the interference effect. And so let's imagine that this is a particular type of randomization. We have 2 treated individuals and 2 control individuals. It's a very simple graph. And you can see that in this graph, each treated individual has a treated friend and a control friend, and each control individual has a treated friend and a control friend. And so if interference only depends on the number or the fraction of treated and controlled friends I have, then definitely if I were to look at the difference between the treated and controlled individuals here, the untreated individuals, I will cancel out the interference patterns, right? Because the interference patterns are identical. On the other hand, here it feels innocuous, right? All I did is I said, treat 2 and 3 instead of 1 and 2 in the same exact graph. But it's very clear now that this one is not good because all of my treated people have only controlled neighborhoods and all of my controlled people have treated neighbors. And so I wouldn't cancel out the interference pattern. So it turns out that some patterns are, some partitions are better than others, right? Some types of treatments are better than others. So can we do this in general? Can we sort of figure out what is a good, we're calling them quasi-colorings, versus a bad one?
How does it cancel out if their interference functions are not the same?
So, sorry. Let's imagine for a second that they're very, very similar, that they only depend on the number of treated versus the number of control friends. That's sort of a simplifying assumption. But even if they're not, as long as they are definitely depend on those patterns very similarly, then that would be enough. So we have some specification results as well that say that you can be a little bit off and it will still do pretty well. All right, so to your point, let's make it simpler. And so our interference now just depends on the number of treated friends and the number of control friends. That's or the fraction. And what turns out to be the case is that we can control the variance or the mean squared error of our estimator. It's really nice. And it has these 3 parts. And what's great about these 3 parts is that they're all things we can control, and we can choose randomizations in order to get these numbers to be really small. So the first part depends only on our partition, and it depends on the differences in the degrees between people you've paired up. So this is because at the end of the day, we only care about now treated degree and control degree. It turns out that if you pair up people who have similar degree, treat one of them and don't treat the other, you're going to do better. That's good. This third part is, again, very similar to that original bias result, right? It's telling us that we only care about individuals that contribute to this mean squared error in terms of individuals who share an edge and who are in my partition set. So make sure to pick partition sets that don't have any individuals who share an edge in the graph. And so it turns out that we can choose this better partition this way by ordering people according to their degree and just pairing them up this way. This will control the first term, and that's the dominant term, essentially. And we can do even better. So this already gives us that mean squared error goes to 0, that we get consistency of this estimator, everything is nice. But we can do even better by then, after doing that, doing a little bit of shuffling and paying maybe a little bit on that first term by getting a huge gain on that last third term. And that's sort of a simple optimization result that we can sort of play around with, and it seems to improve things a little bit. I'll show you just a couple.
It seems here that basically you're getting 1 over n variance, which is what you get if you didn't have any of this problem, right? So
Yeah.
So
What are these K's? And yeah,
it's got to be in there, right? That's the.
So these K's are new Lipschitz constants. They tell you, so K1 tells you a little bit about how important it is to have different number of treated friends, and K2 tells you how important it is, how much of a change in your interference there is if the fraction of treated friends is different. And so these are just control. These are slightly more complicated controls that look like that Lipschitz.
So your problem goes based on the slope of assumptions.
Yeah, so essentially those, I mean, this is sort of where you need to start getting into domain expertise, but you can imagine that it might matter for you that 3 of your friends got treated and not anymore. And so if that's sufficient for you, then that gives us a value of what K1 or K2 is. All right.
Alex,
Yeah. Oh, yeah.
just about the baseball.
Yeah, we need the minimum degree too. D min is the minimum
So
degree.
it's sparse.
So yeah, we have results on sparse networks where this sort of still works. It needs to grow at least a little bit. It's a slightly different result. It's just a little bit more math. But even so, you get a slightly different.
It could be constant usually, or it's could be something else.
So in dense graphs, it's going to go to infinity anyway, right? And so in sparse graphs, the result is a little bit different. You still need, yeah, but you can still get it to work. It's only some, yeah. D min is constant. We're going to run it. It needs to grow a little bit. All right. This is a little bit of a bake-off that I. How much time do I have? Do I have like? Okay, let's skip the bake-off. Under misspecification, we still do well. That's fine. What I wanted to get to is these slides, and there's another one sort of afterwards that I'm not going to get to, but I want to think about how do I leverage the stuff that I've been learning the last couple of days on this. And essentially, one of the things that's missing in there is any kind of decision making by these agents, right? We're not actually taking into account that some people might sort of, to your point, choose to share things or choose not to share things, how they end up doing things. And so that, I think, is sort of an important place where we can start thinking about that, and we can design better experiments by thinking about the strategic behavior of individuals. And I've gained some insight into sort of how to start incorporating. The last point here is that we care about dynamic networks as well. And I'm not going to be able to actually go through the next 10 or so slides of how do you study dynamic networks. But let me just sort of give one, let me go back to this slide. So if you remember, we might have an experiment that's running that some people were told to do one thing versus other people were told to do another thing. And that treatment might change the way in which they interact with the network. And so what's particularly interesting in the model that we've set up, and this is joint work with Jason Shu, who's been here for the semester, and Fan Bu and Alison Aiello, is thinking about a network. So this AIGJFT is a binary indicator of a connection between two individuals at time t, changing as a function, for example, of disease status. So here we're postulating that maybe people connect and disconnect from people in this network as a function of whether or not those people are sick. So if I'm sick, you might disconnect from me. And when I become healthy again, you might reconnect with me. And turns out you can sort of incorporate this into these stochastic epidemic models really naturally by introducing sort of new competing Poisson processes and sort of thinking about this as this complex continuous time Markov chain. We do this sort of in a Bayesian framework. It's hard because there's a lot of missing data. And what's really nice about the work that we've done, I think, is we both have an exact sampler in some settings, and then we have a really sort of efficient stochastic EM to do things that are even harder. But what I want to introduce sort of is this idea that some of these people might have individual characteristics as well. And that is sort of where I think that a lot of the work that we've been listening to the last couple of days can really be leveraged in order to think about sort of actually strategic behavior by individuals. I might disconnect from you, not just in terms because I have a coin toss with a particular probability, but I might disconnect from you because I've been looking for an excuse to get rid of you, right? Or I might not disconnect from you because you're family and I don't care that you're sick, I'm going to help you out anyway. And so that's not captured in our model right now, but it's clearly a very important thing. And sort of in new work with David McAdams, we're thinking about how do you incorporate that in order to study sort of these efficient behaviors of individuals. I'm sorry that I'm skipping through a bunch of slides. These are sort of details of the model, and I'm happy to talk about them later on. In our sort of baseline setting, we studied this particular group of 100 students. We have information about all of their interactions over 10 weeks at 5-minute intervals, right? They all were given cell phones, and the cell phones were pinging when they were in the same room together in the vicinity of each other. And so we have pretty good information about how they interacted. We also have daily information about flu infections, and we have weekly information about recoveries, and also a lot of sort of both both dynamic and static attributes of these individuals. And what we're able to learn, for example, in this setting, is that individuals who are optimal hand washers are less likely to get sick. So that's kind of nice. So wash your hands.
This is mostly like flu.
This is flu-like illness. This is sort of a fairly generous definition of infection because, yeah, but yeah. But why did I tell you all of this? It's because I think these models are way more realistic than the first one that we talked about, right? And I think we need to be able to incorporate this into the experimental design, sort of to leverage these types of much more flexible models. What's nice is that these models give us access to forward simulation. And this forward simulation allows us to think about things like this. So here are some epidemic curves under different strategies of strict quarantine for all, strict quarantine for some symptomatic people, or other types of quarantines that you can introduce. And what's important is that it's not just a single curve. These are stochastic curves that are generated. And so you can see that under strict quarantine, you could do really, really well, right? And squash the infection immediately, but you could also be stuck in the same limbo as you would have been. And so this variability in this is potentially very important when you're designing a policy. And this is sort of an important step in the direction of better policy though. But what sort of the goal here is to now start incorporating agent behavior into the actual modeling framework, and to sort of understand whether or not some of these agents are behaving, myopically, or they're behaving, or sort of they're trying to maximize something, right? There could be some kind of cost of being infected, but there might be benefit to having that link because you might get a job out of it or something. And so how do you incorporate that into it? I'll conclude. I have two more minutes, sort of about this platform that we've been thinking about. So where can we actually run experiments? So the first experiment that we had a campus full of students. It's a closed, essentially, population. We had, I'm saying we, I didn't actually collect the data. This was collected before my time, but probably couldn't run that experiment now, but at the time it was doable. It was about 10 years ago. The second experiment was run on Twitter, and it was really, really hard for us because we needed to collect a ton of information about these people. We weren't working with Twitter, and so we needed to interact with individuals on Twitter, but without actually having control over their feeds. And so we didn't really know what they were seeing. We told them to turn off this, turn off that, but who knows what they actually did. And so what we've been developing, and it's nearly done, and I'm happy to say that it's nearly done. It's sort of an experimentation platform. And this features of this platform allow us to generate social media feeds. And currently it looks more like Twitter than it does like Instagram, but those are sort of just features that are down in the pipeline. And you can designate how individuals are required to interact with the social media environment. You can measure engagement, information flows, and other objects. And so based on the talks the last couple of days, I think that certain things can be measured here. So for example, you can measure value of virality by sort of essentially running the type of experiment that you were describing, Kevin. You can think about sort of effect of connection types on the information flow. So in this platform, the idea is that individuals on board, and it looks like Twitter to them, or it looks like TikTok, or it looks like something, and they're told to engage with it in some way. I'll show you some screenshots of what it's going to look like. You can measure notions of persuasiveness because you can have them engage with each other. You can have them engage with GPT-3 bots, and that sort of is a nice sort of universe to work with. And then you can measure sort of whether or not some types of information or quantification of interactions are more meaningful than others. So this is a previous version of this platform that we built, that we ran some experiments on, and individuals here were just sort of on this platform. They had to have conversations. But the new platform looks more like this. And you, as the researcher, have complete control over everything that goes on in this platform. You can choose what kind of like buttons or dislike buttons to have. You can choose whether or not you display some kind of decomposition of them based on partisanship or based on status. You choose what kind of content is preloaded or written by the bots in the background. So you can have high quality content and low quality content. One of the things we're working on is sort of understanding how these bots will actually perform in real life. I don't know if everybody saw yesterday's ChatGPT-3 that there's some evangelists and some people who have attempted it and it doesn't really work. I think, Ben, did you tweet about not working? Yeah. But sort of we get to sort of control a lot of stuff. And we can decide the type of participants, sort of these bots, or you can have confederates running in there, and you can control sort of all of these things. And I hope
Do people generate content here?
Yeah, so the way that we're going to engage, so the first round of experiments we're planning on running is people are going to be onboarded. There are going to be a bunch of bots in the background that are writing their own content, and the people are going to be asked to generate their own content. They're going to be asked to, this is a universe that you live in now. Please behave like you behave in your regular universe. Things we're interested in are sort of whether or not user choice induces better behavior, whether or not translating sort of from polarized content to less polarized content improves interactions and so on. But I think lots of the things that have been described sort of in a model framework are testable on platforms like this. So thank you very much. This is just some references, and I'm happy to take questions.
Jump right into the next talk, but as the switch is happening, if somebody has a quick question.
Yep.
Can you explain a little bit how the modeling is connected with the causal inference?
Yeah, so yeah, so that's a good question. So that's the stochastic modeling part gives us a realistic model for the universe that allows us to do forward simulation. The reason I'm interested in it is because it allows us to then think about what kind of constant frequency response functions are reasonable in order to design future experiments. So essentially, you can use the outputs of these models in order to design what previously was just partitions. This is probably something else where I would know that the potential outcomes are constant on particular types of choices. It might, yeah, that's sort of the goal. It's easier said than done. I can probably implement it, but I can't. We're working on analyzing that. So we have very partial implications.
Just in time, so she's still getting mic'd up, but thank you very much. So next, I'll do these. So we'll have another 45 minutes. Raj presenting too much data, the prices and inefficiencies in data markets. Take it away. You have until 10:50.
Thanks very much for your invite. So I'm going to talk about too much data, prices and inefficiencies in data market. This is a joint work with Darren Asamoglu, Aso Zaglar, and Annie Makhtoumi, who is in the audience.